It is the second week of July. The ambient temperature is 98 degrees. Your air conditioning unit stops making the low, steady hum of compression. Instead, it emits a flat, harsh electrical buzz. Then, dead silence. The thermal envelope of your home is breached. The house begins to trap heat. You make the call. You pay the emergency weekend dispatch fee. A technician arrives in a pristine vinyl-wrapped utility van. He removes the stamped steel access panel. He attaches his digital multimeter. He shakes his head. The diagnosis is catastrophic. The compressor is locked. The system is fatally compromised. The solution is an immediate full system replacement. $10,000. Financed over a decade. It is an illusion. The compressor is indeed locked. The condenser fan is indeed dead. But the heavy machinery has not suffered a fatal mechanical failure. It has merely been paralyzed. The true architect of this sudden domestic crisis is not a destroyed engine. It is a thin cylinder of stamped aluminum, roughly the size of a standard soda can, bolted to the interior chassis. This is the dual-run capacitor. Its wholesale manufacturing cost is $4.12. The modern residential cooling industry relies entirely on this specific arithmetic. They do not actually need your primary compressor to break. Compressors are built from heavy forged steel, thick cast iron, and dense copper windings. They are incredibly difficult to destroy by accident. Instead, the service industry relies on the predictable, engineered failure of the electrical gatekeeper. When the $4 gatekeeper dies, the $10,000 machine is rendered completely comatose. This creates a perfect asymmetric vulnerability. The technician standing in your driveway is rarely a diagnostic mechanic. He is a commissioned sales representative disguised in a high-visibility uniform. Over the last decade, local, independent heating and air companies have been quietly absorbed by massive private equity firms. You might still see the original family name painted on the side of the van, but the operational model has been ruthlessly restructured. The corporate mandate is no longer maintenance. The mandate is hardware turnover. Their entire business model is built on closing ratios. A dead capacitor on a 98-degree day is the ultimate conversion tool. It creates sudden, severe physical discomfort. It creates an immediate, visceral sense of urgency. It bypasses your logical financial defenses entirely. You are not signing a 10-year loan for a new air conditioner because you actually need one. You are signing it because you want the heat to stop. They leverage the weather against your wallet. The fulcrum of that leverage is the cheapest, most fragile electrical component inside the entire system. You are being held hostage by a mass-produced aluminum can. But to understand why this specific component fails with such absolute predictability, we must stop looking at it as an electrical mystery. We must look at the physical physics of the machine. To understand the deliberate frailty of the modern capacitor, you must stop viewing your air conditioner as an electronic appliance. It is not a television. It is heavy industrial machinery bolted to the side of your house. Inside that steel cage sits the compressor. It is a massive, hermetically sealed iron block. Its job is to violently crush low-pressure chemical vapor into high-pressure liquid. When the system is off, this pump sits at a dead stop against an internal head pressure of nearly 300 pounds per square inch. Imagine a loaded freight train locomotive sitting dead on the tracks. It is stationary, locked in place by its own immense mass. You cannot get that train moving by having a crew of men push steadily against the caboose. Steady, continuous force is completely useless against deadweight inertia. To break the inertia, you need a violent impact. You need a highly pressurized pneumatic ram to slam into the engine block and forcefully rotate the heavy wheels that first critical quarter inch. Once the train is rolling, momentum takes over. It requires very little energy to keep it moving down the track. But that initial kickstart requires terrifying, concentrated force. Your compressor is the locomotive. Standard residential electricity, 240 volts, is the crew of men pushing on the back of the train. It is a steady, flowing river of current. If you send that standard current directly to a dead-stopped compressor, the internal motor will not spin. It will simply lock in place. It will shudder. It will pull dangerous amounts of amperage, heat up, and physically melt its own copper windings. The motor cannot start itself. It requires the pneumatic ram. That is the sole function of the dual-run capacitor. Despite what the service technician might imply, a capacitor is not a battery. A battery releases energy in a slow, controlled chemical trickle. A capacitor is a localized electrical bomb. Inside its stamped aluminum shell, it stores up household electricity, pulling it in and holding it under extreme tension. When your thermostat clicks and calls for cold air, the capacitor detonates. It unleashes an instantaneous, high-velocity surge of voltage directly into the secondary windings of the compressor motor. In the physical sciences, this mechanism is called a phase shift. The capacitor artificially alters the timing of the electrical current. For a fraction of a millisecond, it tricks the standard single-phase power of your home into acting like the heavy industrial three-phase power used in manufacturing plants. It creates a sudden rotational magnetic sledgehammer. The sledgehammer strikes, the inertia breaks, the heavy iron pistons begin to pump, the locomotive rolls. But the capacitor's job is not finished. Once the machine is running, it must maintain a continuous, mathematically precise electrical tension to keep the magnetic field inside the motor from collapsing. It acts as an active shock absorber for the electrical grid. It constantly absorbs and releases microsurges to keep the heavy compressor spinning in perfect, frictionless balance. This continuous cycle of violent discharge and steady absorption generates heat, searing internal friction. In order to survive this brutally hostile environment, the capacitor must be built like a bank vault. The internal materials must be thick. The thermal mass must be dense. It must be capable of containing tens of thousands of miniature electrical explosions every single summer without structural degradation. Historically, they were built exactly that way. But the financial architects of the global supply chain looked at that impenetrable armor and saw an inefficiency. They saw a place to extract fractions of a penny. The modern heating and air conditioning industry does not optimize for longevity. It optimizes for shipping weight and quarterly raw material margins. To understand how your home cooling system was quietly sabotaged, we must shift our focus from the backyard machinery to the offshore assembly line. Inside its stamped aluminum shell, the architecture of a run capacitor is brutally simple. It consists of two long strips of conductive metal foil. Sandwiched between these metal layers is an insulating barrier, typically a strip of polypropylene plastic. This insulator is called the dielectric. These three layers, metal, plastic, metal, are rolled together tightly like a dense spool of ribbon, sealed inside the can and submerged in a protective fluid. The dielectric is the most critical component in the entire system. Its sole function is to keep the stored electrical voltage on one piece of metal from jumping across to the other piece of metal. It holds the explosive tension. It prevents the short circuit. In the mechanical engineering of the 1980s, this dielectric barrier was robust. It was built using heavy-duty plastic film, often measuring 10 to 12 microns in thickness. For context, a single strand of human hair is roughly 70 microns thick. A 12-micron barrier provided impenetrable thermal armor against electrical friction. Then, the global supply chain evolved. The accountants stepped in. Original equipment manufacturers, the corporations whose logos are stamped on the outside of your outdoor unit, began aggressively auditing their component costs. If a corporation dictates the assembly of 5 million air conditioners a year, they must purchase 5 million capacitors. At that scale, the raw volume of polypropylene plastic becomes a severe line item on the corporate ledger. An offshore supplier presents a mathematical solution. They propose stretching the plastic film just a fraction thinner during the extrusion process. If they reduce the thickness of the dielectric barrier from 10 microns down to 5 microns, they cut the raw material cost of the plastic in half. The engineers run a bench test. In a climate-controlled laboratory, the 5-micron capacitor holds the voltage. It starts the compressor. It passes minimum compliance standards. The procurement contract is signed. The cost savings are realized. The margin increases. But the supply chain is a relentless, amoral machine. 5 microns eventually became 4 microns. 4 microns became 3 microns. This is the economics of the micron. Global manufacturers shaved fractions of a single cent off the production cost of an aluminum cylinder. In doing so, they mathematically guaranteed the failure of your air conditioner. When you thin an electrical barrier, you physically lower its resistance to heat. This is a rigid law of thermodynamics. On a July afternoon, the ambient temperature outside your home is 98 degrees. Inside the steel cage of your condenser unit, baking in direct sunlight, the operational temperature easily climbs to 150 degrees. The 3-micron plastic barrier cannot withstand the thermal load. The material softens. The continuous, violent surging of electrical current creates internal friction, generating even more heat. The plastic degrades. Eventually, a microscopic pinhole burns straight through the thin dielectric film. The tension breaks, the positive foil touches the negative foil, the stored energy discharges inward, instantly boiling the surrounding protective fluid, the internal pressure spikes. The top of the aluminum can bulges outward, splitting the circuitry. The electrical gatekeeper dies. The compressor goes blind. The house turns into an oven. This is not a manufacturing accident. It is intentional financial calculus. The part was designed to the absolute lowest threshold of physical survival. The fact that this calculated fragility leaves fixed-income homeowners stranded in dangerous summer heat is not a structural concern to the manufacturer. It is simply a secondary market opportunity for the service sector. Your memory is correct. You are not romanticizing the past. You are remembering the mechanical baseline of a previous era. You remember the square, olive green condenser unit sitting beside your childhood home. It rattled. It was inefficient, but it ran for 30 years without a single service call. Today, a modern system fails in 5. The difference is not bad luck. The difference is mass. Look closely at the run capacitor of a legacy air conditioning unit built in the 1980s. It was not a hollow aluminum soda can. It was a dense, heavy block of drawn steel. It weighed 3 times as much as the modern equivalent. That weight was not arbitrary. It was thermal armor. Inside that steel casing, the electrical coils were not separated by 3-micron plastic. They were separated by heavy layers of engineered craft paper and thick polymer sheets. More importantly, the entire internal cavity was flooded with a dense, viscous dielectric oil. This liquid served a singular, vital mechanical purpose. It was a structural heat sink. When the localized electrical bomb detonated to start the compressor, it generated a violent surge of thermal friction. In a modern capacitor, that heat has nowhere to go. It bakes the thin plastic. But in the legacy capacitor, the heavy oil immediately absorbed the thermal shock. The fluid wicked the heat away from the fragile electrical foil and transferred it outward into the thick steel casing. The steel radiated the heat safely into the atmosphere. The internal temperature remained stable. The components survived. It was an elegant, indestructible application of fluid thermodynamics. It allowed the capacitor to endure decades of brutal summer heat waves without structural degradation. Then, the regulatory landscape shifted. In the late 1970s and 80s, the Environmental Protection Agency began aggressively targeting the chemical composition of dielectric fluids. They cited valid ecological concerns regarding soil contamination and the toxicity of polychlorinated biphenyls and heavy mineral oils. They mandated the removal of these traditional fluids from industrial manufacturing. This regulatory intervention was a gift to the corporate accountants. The environmental mandate provided the unassailable excuse to dismantle the heavy-duty architecture of the run capacitor. Manufacturers did not invest capital to engineer a safer, equally dense replacement oil. They simply removed the liquid heatsink entirely. They transitioned to dry capacitors. They replaced the thick craft paper and heavy oil with the micro-thin bare polypropylene film we see today. They swapped the thick steel casing for tissue-thin stamped aluminum. They eliminated the thermal mass. They stripped the component of its ability to absorb heat. They branded this change as an ecological victory. They marketed the new units as environmentally compliant. To mask the obvious fragility of this new dry design, engineers introduced a process called metallized film. They spray a microscopic layer of zinc directly onto the thin plastic. When a power surge creates a short circuit inside the modern capacitor, the heat instantly vaporizes the metal around the microscopic puncture. The industry calls this a self-healing feature. They market it as advanced technology. It is a deception. Every time the capacitor heals a puncture, it burns away a fraction of its own conductive surface area. It loses a fraction of its total electrical capacity. It slowly bleeds to death, micropuncture by micropuncture, over a period of 36 to 60 months. It is controlled, engineered degradation. The physics of electricity had not changed. The thermal load required to start a heavy iron compressor remained constant. The heat was still there. Only now, the armor was gone. By removing the thermal mass under the guise of environmental progress, the industry achieved 2 distinct corporate victories. They drastically reduced their raw material shipping costs, and they quietly introduced a highly predictable, mathematically certain failure point into every single air conditioning system manufactured in the modern era. The sudden failure of your air conditioning on a July afternoon is a severe inconvenience, but a cleanly ruptured capacitor is not the worst-case scenario. A sudden death is an act of mechanical mercy. The true danger lies in the slow decline. Remember the self-healing technology of the modern plastic film. Every time a microscopic puncture burns through the dielectric barrier, the part heals itself by destroying a tiny fraction of its own conductive metal. It survives the thermal hit, but it loses a fraction of its total electrical capacity. In the industry, this capacity is measured in microfarads. A brand new capacitor might be rated for 45 microfarads. That is the precise volume of explosive tension required to safely start your heavy iron compressor. Over 2 summers of heat waves, the internal micropunctures accumulate. The metal film burns away. The capacity bleeds down to 40, then 35, then 30. The part is not completely dead. It is still sending an electrical charge. But the tension is compromised. The pneumatic ram has lost its pressure. When the thermostat calls for cooling, the weakened capacitor detonates, but the surge is anemic. It strikes the heavy stationary compressor, but it lacks the violent force necessary to instantly break the resting inertia. The locomotive struggles to roll. The heavy iron pistons hesitate. In the electrical sciences, this hesitation is catastrophic. When an electrical motor is locked in place but receiving power, it draws an immense surge of current called locked rotor amperage. This surge generates instant, searing heat inside the copper windings of the motor. A healthy capacitor breaks the inertia in a fraction of a millisecond. The heat dissipates harmlessly. A weak capacitor leaves the motor locked for a full second, or 2 seconds. The copper bakes. The motor eventually stumbles into motion, but the torture does not stop. Remember that the capacitor must also maintain a continuous electrical tension to keep the spinning magnetic field in rigid balance. A degraded component cannot hold the balance. It creates a sublethal electrical drag. It forces the compressor to run with a continuous invisible limp. Imagine driving a heavy pickup truck down the highway in third gear while riding the brake pedal. The engine will not immediately explode. It will continue to drive, but the internal friction is staggering. The transmission overheats. The fluid breaks down. The mechanical wear accelerates exponentially. This is the precise mechanical reality inside your $2,000 compressor. The weakened $4 capacitor forces the primary motor to pull excess amperage every single minute of its operating cycle. The excess amperage translates directly into thermal friction. The internal temperature of the steel housing spikes. Inside the hermetically sealed compressor, the copper motor windings are coated in a thin layer of protective lacquer. Under the continuous heat of a struggling capacitor, this lacquer begins to bake. It turns brittle. It flakes away. The bare copper wires vibrate against each other. Simultaneously, the protective lubricating oil inside the compressor begins to boil. High heat chemically degrades the oil. It turns from a slick lubricant into a corrosive, highly acidic sludge. The acid eats into the mechanical bearings. The steel grinds. This is a silent execution. It happens completely out of sight. Your house is still cold. The air conditioner sounds relatively normal. But inside the steel cage, the most expensive component of your home infrastructure is being systematically tortured to death. By the time the cheap plastic capacitor finally ruptures and the system shuts down, the damage is already permanent. The service technician arrives. He replaces the $4 part. He charges you $300. The cold air returns. You think you have won. You have not. The technician knows the mechanical reality. He knows the compressor motor has been baking in its own acidic sludge for 6 months. He knows the copper lacquer is compromised. He knows the structural integrity of the machine has been fatally undermined. He does not warn you. He simply hands you the invoice and drives away. He knows he will be back next summer. Not for a $300 repair, for the $10,000 replacement. The financial trap is structurally complete, but it is not inescapable. You can break the cycle. You simply have to strike first. The defense against this engineered failure is not an annual maintenance contract. A maintenance contract is simply a corporate financial instrument designed to monetize your anxiety. The true defense is preemptive, mechanical intervention. You must sever your reliance on the offshore supply chain. You must replace the engineered failure point before the microscopic degradation even begins. Do not wait for July. Do not wait for the system to flatline. Walk outside to your condenser unit. Disconnect the main power disconnect box on the exterior wall. This is a non-negotiable physical requirement. The machine must be entirely dead. Remove the stamped steel access panel. Locate the dual-run capacitor bolted to the chassis. Take a clear photograph of the data sticker printed on the side of the aluminum cylinder. You are looking for 2 specific data points. First, the voltage rating. It will read either 370V or 440V. Second, the capacitance, measured in microfarads. Because it is a dual capacitor, tasked with regulating both the heavy compressor and the smaller condenser fan, you will see 2 numbers separated by a slash. For example, 45/5 microfarads. This photograph is your mechanical blueprint. Do not purchase a direct replacement from the original equipment manufacturer. If you buy the exact same brand, you are simply buying another 3-micron plastic time bomb. You must source a heavy-duty, domestically manufactured capacitor. Look for units explicitly marketed as motor-run capacitors built to the rigorous EIA 456A standard. These premium units fundamentally reject the economics of the micron. They utilize thicker, heavier polypropylene film. They utilize thicker external metal casings. Some domestic manufacturers have even reintroduced heavy epoxy or proprietary oil-filled designs specifically to act as thermal heat sinks. These premium components do not cost $4. They cost approximately $30 to $40. This is the most powerful asymmetric financial leverage you possess. A $40 preemptive strike completely neutralizes a $10,000 systemic threat. Installation requires strict mechanical discipline. A capacitor stores lethal electrical voltage, even when the primary utility power is disconnected. You must bleed the residual charge. Wearing heavy gloves and using an insulated screwdriver, bridge the metal terminals at the top of the can to short the remaining electricity. It is a simple, physical transfer of stored energy. Once the charge is completely neutralized, transfer the wires one by one from the old, fragile unit to the heavy-duty replacement. The terminals are explicitly labeled. C stands for common. Herm stands for the hermetically sealed compressor. Fan stands for the condenser fan. The geometry is undeniable. It requires no specialized diagnostic equipment. It requires only strict mechanical compliance. Secure the new component to the chassis, replace the steel panel, restore the main power. You have just fundamentally altered the operational lifespan of your primary cooling infrastructure. You have restored the violent, unyielding electrical kickstart your compressor requires to safely break its resting inertia. You have eliminated the sublethal thermal drag. You have halted the internal acidification of the compressor oil. More importantly, you have broken the behavioral loop. The private equity firms that rapidly consolidate local heating and air services build their revenue models entirely on your presumed ignorance of basic electrical physics. They rely on the mathematical assumption that a dead machine in 98-degree heat will force you into immediate high-interest financial submission. By taking mechanical control of the Gatekeeper component, you remove their leverage entirely. You separate your physical comfort from their corporate profit margins. You reclaim absolute sovereignty over the thermal envelope of your home. The machine belongs to you again.